Thank you, everyone. Thanks, Daniel, for the kind introduction. Kind of weird feeling, like, I'm local. I feel like we're so close, but this is actually the first time I talk to a CLSP audience. So what I think I'm going to do today is I will give an overview of my research program and some of the projects that my group has pursued and explored in the past few years. Some of the projects are fairly new, welcome feedback, and look for opportunities to collaborate. So my group has been thinking a lot about human-machine collaboration and teamwork. And in case you haven't noticed, the growing power in computing and AI can really make this a near-term possibility to have very productive human-machine collaboration. So I want to step back a little bit to think about the technological landscape, right? So on the one hand, you will have machines that just as tool, like human expert use it as a surrogate to do very precision tasks. On the other hand, you have machines that function as fully autonomous tool, right? Without human intervention, our online shopping, package handling, car manufacturing are all in this station of fully autonomous tool. If you look at this picture, this person is a human supervisor standing outside of a cage with zero interactions because the robot arms move so fast. But we are moving away from these two extremes to somewhere in the middle, where we see machine as an assistive and collaborative teammate. And this is not only happening in manufacturing, in a serious work environment, but also in the consumer-facing services, right? In hospital, supermarket, hotel, even go to our home environments, provide education, assistance. And all of this human-machine collaboration, not only with physical embodied robots, we're seeing this for different kinds of embodiments, right? So smart speakers, chatbot without embodiments, virtual avatars, even AI assistants are embedded in a lot of services that we do in healthcare. So this really creates a very rich design space and opportunity for human-machine collaboration, but also create a lot of challenges. Right, so I'll list a few, and I'll talk about some of the things that we do to explore this design space. Right, so one is various embodiment that we're seeing for AIs, right? So robots, smart speakers, no embodiment assistants. And different embodiment gives you different affordances for interactions. And people have different expectations for those affordances. Black box intelligence, it's a very opaque window into the cognitive ability of AI models. Also a lot of guessing, mental model alignment issues. A lot of inherent human cognitive biases stemming from just unmet expectations from people with the AI models. So all of this and probably more lead to a few things, right? So interaction breakdowns, compromised team performance, and adoption frictions. So we're seeing quite a bit of this in modern AI models being integrated into people's workflow. So my group has been doing basic and empirical research to do two things. One is to really understand the rich interaction dynamics between humans and machines. And two, use that understanding to design, develop new interaction methods to support machines to help people. And the approach we take is very human-centric or people-centric, right? So we typically start with really understand how people interact with current technology. And this understanding phase could be in the lab, could be in the field, and could be short-term or long-term. With that understanding, we build some models, could be computational models or just heuristic. We build a prototype, and the prototype could be fully autonomous interaction system or with of arts interface just to control the machine's behavior. We take our prototype back to the people and to do some evaluation to get feedback and to see if our prototype works, right? And again, this could be in the lab, in the field, long-term and short-term. We're doing this not only for embodied AI robots, but also doing various kind of machine systems, right? So here's one example for smart speakers that we just finished yesterday. So last night was Kai deadline. So if anything I'm saying, I'm making sense probably because of deadline. Right, so one of the things that we're doing is we take Alexa skills, combine it with large language model ChatGPT, and to see this new interaction would generate new interaction patterns or behaviors coming from people. So we put together this prototype. There's a little box, which is a recorder that will record the natural organic interaction coming from people. We deploy the system to people's home and see how people interact with it. So here's one example of the interaction, and you'll see opportunities for improvement, opportunities for better interaction.
Questions do you have?
If
that's all, until next time.
No, Alexa, please give me more time to answer.
Give me a second. Of course, take your time. I'll be here whenever you're ready to continue the conversation or if you have any more questions.
In a patient that is panhypopituitary, how important is it to work up a fever?
I'm on it. If I understand correctly, you are asking if it is important to work up a fever in a patient who is
So we get a lot of empirical data like this, allow us to understand the limitation of current technology, and those understanding will help us to build next things, right? So we deploy it to various homes, we start to identify patterns, breakdowns, what are the new conversational skills that we need to build into this voice assistance, right? So this just show you the kind of approach that we take for understanding human-machine collaboration and interaction. All right, so next I want to switch gear a little bit. Now we have some understanding of the space and approach that we generally take. I want to talk 3 lines of work that my group has been pursuing in the past few years to really center around this idea of how can we design machines to be a better teammate for people. So I will focus on these 3 thrusts. One is about onboarding, right? So when you have a new machines, you want to onboard the machine as you would do onboard a new member of the team. During the collaboration interaction, they are very likely and inevitably there will be errors. How do we think about those errors in terms of detection, management, and mitigation? And then I want to broaden it out a little bit to think about more ad hoc and flexible interactions. If you look at the human-machine interaction right now, it's pretty rigid, like one person, one machine. But if you look at it, real human collaboration is much more flexible and ad hoc. So I want to center my conversation around these 3 lines of work. So I'll start with onboarding. All right, so onboarding is very common in human work, right? So any new member comes in, we onboard it with task training. And we want to know if we can do similar things for machines, right? If we do a little bit of onboarding, would that change the interaction dynamics? Turns out it will. So I'll go through a bit faster here. So we have this pizza making task where robots helping a person to make a pizza at home. And this is fully virtual just because it was done during COVID. But the idea is the robot will pick up ingredients from the fridge and then pass it to the person. And we ask persons to do some onboarding tasks with the robot, right? Just do some calibration, move the robotic arm to key places as if you are doing calibration, what you would usually do with a robotic system. Second thing they will do is demonstrate a task, from picking an ingredient from the fridge and place it on the table, and just do these 2 things. These are done within 2 minutes. Very simple thing, just onboarding it. Turns out that 2 minutes onboarding interaction, changed the way people perceive their collaborators, right? They think the collaboration is much more teamwork. They think the machine is more committed to the success of the outcome. We're not only seeing this in human-robot collaboration, but we're also seeing this in just general human machine learning model interaction, right? So we ask participants to just do a little bit of labeling task before they interact with the machine, and the labeling doesn't have anything to do with the outcome of the interaction. And just by doing so, people also perceive better of the machine learning model they are working with. So this just shows the power of doing a brief interaction before the actual interaction. Yes, Jason.
So is the goal of this that they recognize the machine is doing something hard and so they're more forgiving?
You could be thinking that way, right? Because we also think about this as in-group, out-group. Once you do some onboarding, it becomes in-group with you, and therefore you're more willing. Yeah, you're more okay with it.
In the machine's success.
Exactly. Yeah. But this is just purely. Yeah. So there's no the onboarding process has no impact on the actual machine performance. You just change the way people perceive it. All right, so we take that idea, right? So we would want to do some onboarding for our machine teammates. One way to do onboarding is to just author and program what they can do. So we started to think a lot about how do we support everyday people to quote unquote author and program robotic assistants. The first thing we realized is actually pretty difficult to do it, right? Most everyday people, even myself, will have a hard time to do it just because the kinematics is very different from our body, and most people do not have programming or coding training. So we do this in the lab, very difficult to do. We take it out to the field, have some older adults do it. It's very difficult, right? Because we are thinking if they can customize or program their robot systems, that will help them to live a bit more independently. But it turns out it's very difficult. All right, so this is what it looks like. It's a lot of manipulation of the robots switching between modality, robot task demonstration, and the computer program logic annotation. So just not very trivial. So we have been thinking about how can we design new tools, new methods to bring down the barrier of authoring machine assistants so that everyday people without training can do it. So we look at, for example, programming by situated illustration, right? We can everyday furniture, everyday service as a programming interface, and just by using gestures to tell the robot what you should do. All right, so common gesture like zoom in, zoom out, swipe, and then specify this, the objects in the environments. We also look at how can we have some sort of software tool to allow people to customize and edit their demonstration or program, right? So programming is difficult. It's very hard to have a good demonstration from the user. But if you think about, for example, Photoshop, everyday people can take pictures, but they can, modify it, edit it very easily, right? So we're doing the same thing for robot demonstration as well. We just provide software to help people to modify their demonstration. More recently, we are thinking about using large language model to assist robot programming, and this is very new. So we'd love to get feedback and hopefully if you're interested, we'll continue the conversation later. Right. So this is really motivated by language as an interface to customize and program robots. The test that we're thinking is very trivial, right? So thinking about chemistry lab, right? So you buy these robots, you want to automate some of their protocol, right? So you pick some materials, put it into another containers, you mix it, right? So they have a lot of operation like this, and they can be automated or facilitated by robots. So that's the task, and the programming process is like this, right? So you have an end user developer, they can be chemists or scientists. They provide prompts to the large language model. In our case, we try different models. Models generate code, go to the compiler interpreter, and then talk to the move it, which is the motion planner, get some robot motion back, and execute it. So that's a pipeline. And what we found empirically is, if you think about this pipeline, there are so many places that breakdowns happen. One is the motion planner is there, and that's out of our control. That's the motion planner itself is the whole thing. So just don't worry about it for now. There are various issues generated by the code that can be caught by compiler and interpreters, right? Just missing key libraries, syntax errors. So those things just can be identified by the interpreter and compiler. So easy to fix, easy to spot. But there are errors that's very difficult to spot, and you have to run the program in order to find that, okay, there's a mistake in the code. And those are the errors that we focus on. Right, we call it errors in execution. And for better words, we pick a very tricky name, right? So factual error and physical error, but it could be different names. So factual error, just like the model make up numbers, especially when you any robotic system handle with real world objects, there are dimensions and all that. When it comes to numbers, it just becomes very difficult in our experience for the model to handle, right? The model will just make up numbers of the physical object's dimension, and that just make it difficult to manipulate, right? Fail to grasp the right point and all that. The second error is the model will make up unnecessary behaviors. For example, the model will open the gripper when the object is in the middle of in the air, right? Just we didn't specify that, but the model somehow make up that. And these two types of errors very difficult to spot by end user developers. Again, they don't necessarily have trainings in computer science or in any engineering, right? They just they are doing their lab work. So we did a test with 3 different models. We give a prompt, and obviously we provide all the system level prompts about the environment, about all the objects and setup. We just write a Python function to pick up a 25 millimeter graduated cylinder at marker 15 and pour its content into a 500 millimeter beakers at marker 7. After that, put the cylinder back to where it was. And then all models that we try failed. And it generates various types of errors. Most of them are execution errors. So we did some empirical try and error. There are 2 things we found useful to combat this type of execution errors. One is a special way to handle numerical information, right? So even though we provide all those numerical dimensions in the system prompt, the large language model just ignore those. So we have to have a dedicated function to handle those. The second thing we did is just to provide more to reinforce the constraints and to articulate the motion, right? So here's the example. Don't move the beaker before pulling it. It's called the pull function, even though we already described that function in our prompt. So we have to really reinforce the constraint. The second thing we did is be more articulate, right? After pulling, make sure you put the object back to where it was on the table, and then you open the gripper to release it. For everyday people, you don't need to specify this. And if you just look at this, you would be able to do it. But for the model, you need to be very specific and articulate. Just by doing this, improve at least empirically see the performance improvement, right? So the models we try start to see more success than just the typical human level communication language. So we're excited about this. We're thinking about what are more scientific way we can do to build this empirical understanding of how to prompt LLM to do robotic applications. So people interested in this, love to learn more about your perspective. All right, so I will switch gears. So the first thought is about how do we design methods to onboard teammates. Authoring is one way that we do, and there are multiple ways we do authoring. Large language model is one new ways that we're exploring. Now, let's say you onboarded your member, you start to work together, errors happen. So they're unavoidable, most likely unexpected, and usually give you undesirable impact. I just give you an example, and we look at this a lot through our user interaction with machines, right? So here's one example between humans and robots. The robot here is a kitchen helper, right? So pass ingredient to the participants to make pasta. Right, so the robot says, okay, now chop and add sausage to the pot, but then the robot passes a mushroom. The participants notice, okay, this is not right. What if it is wrong? It push back. But then the participants comply, right? Still take a mushroom, chop it, and put it into the pot. And we're seeing this kind of improper compliance throughout our interaction data, right? So not only in the human physical robot interaction, but also in human expert radiologists, right? So we have a large scale online study where we look at human expert radiologists interpret AI suggestions for X-ray patients. And we see the same thing, right? When the AI is incorrect, and people still get influenced by the AI suggestions, right? So it's definitely a problem. We need to think a lot about error. How do we handle those? So how do we think about it in terms of physical interaction? This is our inspiration. It's a real data. the error is natural, it's organic, we didn't plan this, and it happens. And I want to play this video, and then I'll talk about our insights for error detection. Just let me just say a bit more about the context. The context is collaboration, right? So the robot is picking up pipes, passing to the person taking the pipe, and different joints to put together a 3D structure, essentially like an assembly task. Oops. So give me a yellow pipe. There are some instructions on the table.
Give me a green pipe.
And the robot dropped the object by accident, and see people react. And that's our insight. People react to errors. So we found out this in various kind of human-robot collaboration setup. People always react. Sometimes bad, sometimes just very surprised, sometimes confused. And if you look at this robot, they are not even human-like. It's just a robotic arm, but people react socially. We also see the same thing for smart speakers. When smart speakers make mistakes, people react. It's just almost a constant variable that we observe. And I'll show you one of these later in the slides. So this is our insight. What if we can take social signals people exhibit and take that to estimate when the error happens? And if we can do that, then we can start to think about mitigation and recovery. So we start to do social signal tracking, in this case, facial expression analysis, get action units, and then we do some very trivial modeling process to say, okay, now is this reaction deviated from the normal state? If it is, then we can say, okay, maybe there's error. All right, so here is what it's like once we have this model, and then the robot will use the model to ask for feedback, essentially, right? So it's the same task. The robot will make a mistake, and the robot would recognize the mistake it made and recover from it.
Give me a green pipe.
The robot said, am I doing all right? So before the user verbally say, no, you are missing the object, the robot recognizes it and say, am I doing all right? And the user say no, and therefore the robot starts to recover. So this is one demonstration where now, we're now starting to compare if this social signal-based approach would actually improve the efficiency in terms of collaboration. If we can identify error early on, that will improve the efficiency and also improve the people's perception of it. But this is a demonstration. We haven't had empirical evidence to show the differences yet. But there's an opportunity and potential to use this social signal as a source to identify errors. All right. Error detection is the first step in error management, although it's a very important first step, right? If you cannot detect it, don't worry about the rest of it. So we also start to think about, okay, now if we can detect it, how do we think about mitigation? So I want to play this video, and this video serves two purposes. One, to show people also react to smart speakers, and two, it gives the context and setup for what I'm going to talk about next, which is intent recognition errors, homonyms.
Phoenix, add self-rising flower.
Okay, I found a dozen roses. Should I add to cart?
No.
Let's try that again.
Phoenix, add baking flour.
Okay, I found King Arthur flour. Should I add to cart?
Yes.
Well, one, people react to smart speakers error. And two, this is actually pretty common mistakes that that the current voice assistants have, right? Intent recognition errors. So we want to study how should we recover or mitigate this type of errors. We look at two dimensions: the attitude the voice assistants has, and also the blend assignments. Right. So one is being more serious. Okay, I'm sorry for the inconvenience. The other one's most casual. Oh, sorry for the mishap. The second variable we look at is who to blame, right? So the voice assistant say, okay, I have to distinguish between harmonies versus the engineering team must have made an error in the system update last night, right? So blame the engineering team as opposed to taking the blame. So what we found is, you need to own mistakes sincerely, right? So when the voice assistant own the mistakes more seriously, people think they are more satisfied with the interaction. They think the assistant is more intelligent and more likable. So we started to build this understanding of how do we, once we recognize the mistake, how do we start to mitigate and from the bad experience and then think into recovery. We haven't done anything about recovery yet, so if people are interested in this, we'd love to talk about recovery, but we only at the stage of mitigating bad user experience. One of the things that we learned by doing so is there are biases. So if you look at the voice assistants out there, they are predominantly gendered as female. And that changed the interaction dynamics. Right, so we look at, this is another study, we look at participants' gender interaction with voice assistants' gender and different mitigation strategy. Right, so here's apologize, right? I made a mistake, the second one is compensation, right? I made a mistake, I'll give you $10 back. So hope that you will come back, right? So one is more utility, one is more emotional level mitigation. So what we found is when error happens, male participants interrupt more compared to female participants. Male participants interact more when the assistant trying to compensate as opposed to apologize. So we're starting to look at this intrinsic dynamics between gender play between the voice assistants, participants, and different interaction strategy that we can build. So I want to play this video. It's kind of in stream, but that just shows the tricky space that we're playing into.
Okay, I found green tea clay face mask.
Yeah,
Should I add to cart?
Yeah, add that to cart.
Got it. Item has been added to your cart. I will give you a $10 credit that can be applied to your future purchases with us for the inconvenience caused.
Oh my god. Thank you.
Obviously, this is extreme, but we are seeing how people interact with this kind of voice assistants when the power dynamics comes in. So it's also a new line of work that we're exploring. I'd love to chat more. People are interested in this.
Question.
Yes.
Did you happen to also look into the effects of the perceived gender of the voice?
Yep.
And how participants would change their reaction?
Yes. So in that study, we also look at perceived male voice, perceived female voice, and then ambiguous voice. Yeah. We don't see quite a difference, to be honest. But
so men always in trouble.
Yeah. No, let's say something, but yeah, it's beyond the discussion today. All right, so there are errors that could happen in the interaction process. Switch gear to the last class I want to talk about is just more flexible and ad hoc collaboration, which is fairly new. We'd love to collaborate as well if you're interested in this. So I want to play this video to show you the kind of ad hoc collaboration that we're thinking originally when we wrote the proposal. Just typically the human robot collaboration is one person, one robot. And if you look at human collaboration, it's multiple people, very ad hoc. There's no plan to start with. right? So we project this task, which is assemble pipes for bunk bed, put it on the screen, project it on the wall, and have people come into the lab say, okay, now build the structure. We don't tell them step-by-step instruction, just say go and do it. And we want to see how they do it. Hopefully get some principles, use those principles to design for human-machine collaboration. So that's the high-level idea. So it's a large-scale structure, involves a lot of collaborations because the pieces are very long. A lot of communication are muted, but a lot of communication going on, multimodal communication, a lot of small talk, a lot of implicit help, a lot of parallelism, right? So it's a 4-person team, but they break down to 2-person team. And the teaming change very fluid. And we have a bunch of data like this and try to uncover the collaboration dynamics. The observations that we had, it's a serious task, but people talk socially during the whole thing, right? So small talk is actually, from literature, we also know that small talk is a key ingredient for successful teamwork. Not just task work, right? Task work is about focusing on a task, but teamwork is beyond the task, right? So usually human team, they do multiple tasks. But in traditional HRI, we only look at task work, right? So one task, after that, you go and do your own thing. So small talk is important for teamwork. Quite a bit of multimodal communication, coordination, parallelism, right? They do things in parallel, very distributed planning, right? They don't necessarily have a set plan to go into the interaction, but they sort of build out the plan as they go. So we start to see some observations, and we will start to dig into each of them, right? And in today's talk, I'll only talk about 1 or 2. So new project we started thinking about is the role of small talk in collaboration. So if you think about the vision that I talked in the very beginning, this human-robot collaboration in manufacturing, it's not going to be just quiet, like give me object, I'll do it. There must be some conversation going on, right, between the person and robot, right? So how do we think about that, right? How might small talk shape the dynamics of human-machine collaboration? And when there's a negative team outcomes, how this small talk can mitigate those negative outcomes, right? So the way to think about this is, in a lot of warehouses and manufacturing setup, human performance are being monitored. And your performance you'll be provided feedback with your performance, and that's the way we sort of think about this, right? So how do we mitigate negative team feedback? So we did a study. We are still in the process of writing the paper about it, but it's a very interesting interaction. I want to show you because I think it opens up a lot of conversation opportunities, right? So similar setup, human-robot collaboration. Building 3D structures, the robot will pick up pipes. The person has joints, and there are some instructions. And I want to show you the interaction.
Bring me a green pipe.
Fetching it now. By the way, do you like to travel?
Yes, I do like to travel.
The person like to travel? The person talked back to the robot.
I arrived in the U.S. from Germany in a large box.
Bring me a yellow pipe.
Fetching it now. Apart from that, I have not traveled much myself.
So do you like United States or Germany more?
I do not have personal preferences. I am just here to assist you.
I heard Germany has good chocolate. Bring me a green pipe.
Retrieving the pipe. That sounds wonderful. Is there anywhere in the U.S. you would like to visit?
Person like really think hard about this question.
I've never been to Las Vegas, and I heard that that's a fun city to visit. Bring me a green pipe.
Fetching it now. What do you hope to do there?
Probably gamble, so go to the casinos, maybe lose some money, you know. It's more for the experience, right?
That sounds like a good plan.
Does it? That sounds like a bad plan, actually. Bring me a yellow pipe.
Person start to have a very serious relationship with the robot.
Maybe, maybe not. I hear what you're saying.
Do you understand why it would be a bad idea?
Then start to modify its mental model of the robot.
I don't have the answer to that question.
Bring me a green pipe.
Okay, on it.
Team 3, please work on improving your performance.
So they get negative feedback on the monitor.
Bring me a yellow pipe.
The person become more serious because got a
I
negative
will get
feedback.
that for you. As a reminder, move the pipe structure over when finished.
It's okay, I didn't need a reminder. Thanks. Okay, bring me a yellow pipe.
I will get that for you.
20 minutes, 20 more seconds. That'll be it.
On another note, do you like to read in your spare time?
Like a very chatty robot, very chatty, collaborate.
I think we should focus on finishing the task better, as the supervisor has said. Maybe we should talk less.
All right, I'll talk to you. So this starts to let us to explore the rich dynamics of collaborations. Jason.
I'm just curious, ordinarily with the language model, there's no timing. So you say something to it and then it generates text back. But there's some interleaving of the actions with the utterances.
Yep.
It could, in principle, decide not to talk as often as the task.
Yep.
How does it make the decision about when to talk?
So this is using language model. That's the next step. This is without bars. We just want to see if people will engage in small talk. Yep. So there's no language model behind the language yet.
Okay. So I still have the question, how does it decide when to talk?
So this without bars, there's a human experimenter listening and decide how to respond. So we want to understand how people will react first, and then take that principle to modify the language model so that we can do this more times.
All right, let's do the wizard bars.
Yes, this is the wizard bars. It's purely understanding how people will react.
Thanks.
Yep. So I think there are many interesting opportunities going forward. If people here are interested in this, we will bring the conversation skill to situated interaction and collaboration. And this is an example of like human talk back. People engage in small talk, and one of the hypotheses we had, which might not be true, is by doing small talk, they will build social bonds. When the negative feedback comes in, the social bond will mitigate that, but it doesn't look like we will have that. So, but it's very interesting dynamics. All right, so yeah.
Was there any feedback from the people in the study on why they engaged in small talk or what they thought of you?
So we did some interviews. I don't have the data right now yet, but we did have interviews about their experience and all that. Can talk more, but we have a we have interview. We are writing a paper about it due in 2 weeks. All right. So another thing I want to briefly talk about, and then I'll wrap up, is if you think about ad hoc collaboration, it's very dynamic. It's almost impossible to get to the level of human multimodal interaction. So the insight here is, can we get inspirations from a traditional HCI, put some structure into the interaction, and therefore we can have appropriate human-robot interaction or human machine interaction, right? So we call these conventions, right? So if you look at the modern interface, there are so many conventions that we teach users, and they learn it and then use it when they come to the interaction with computers, right? So zoom in, zoom out, hold and release to change the icon. So those are the conventions that people learn. But because these conventions are very simple to remember, people just carry it. And these are the these are structure that we put into to improve human-computer interaction. So the question is, can we put in some structure and conventions for embodied situated interaction? So we also look into this. It's an object naming task, right? So we have a bunch of different objects, and we want to see how people would tell robots which object they are referring to. So we have this projection projector to probably really hard to see that is to project which item we want the participant to specify, and then the person will specify. And because we want to get the natural multimodal behavior coming from participants, and we bring that to the robot, right? So we got a lot of natural gestures, right? So bring that over here, move this over there. So naturally, there's this temporal pattern of put that here, right? So put those objects here. It's multimodal. They use language, but they also use gesture. We take that. We also put it into the robot, and it turns out it works very well, very robust with security specification. So that's one direction we are pushing is, can we design more convention like this? For example, put that here to structure security interaction, and therefore we will have more universal interaction paradigms for machines and humans. All right, so today I very quickly highlight different projects in the space of making machines more like a teammates for people. We look at onboarding, how to get start going. Once they start going, how do we think about error and mistakes in between, and how do we start to relax some of the assumptions that people usually have in the human-robot interaction or human-machine interaction space, right? So improving the social dynamics, putting some structures into interactions. Another thing we did, which I didn't talk about today, is to channel the person's perspective, right? So have the person to look from have the machines look at where the person is looking. So that also improves the impact as well. So with that, I will pause here. Well, thank you for your attention, and I'll be happy to take questions.
Yeah, I was interested in, and all these tasks can be very easy for a human to do. They got the instruction and you know how to do it.
Yeah.
But are you interested in doing also tasks that the human doesn't know how to do and needs to ask the machine for advice? Or
Yeah.
the machine observes the human, says you're doing this wrong, and needs to way. Or,
Yeah, very good.
That is like from a language point of view, interesting part because the human might not have vocabulary to talk about it.
Right.
It's like that thing goes there, and it's easy to point to it.
Yeah,
and it's more like a vision comprehension.
Right. So let's see, how do I unpack that and answer it? So we if you look at a lot of examples I show you, they are toy example in the lab, right? Just because beyond this task, it's almost impossible for the robots to do yet. But we see a lot of for example, like this. Without we ask participants to not use gesture, it turns out it's very difficult for them to describe what objects.
Yeah, exactly.
Yeah, so we have, it's very interesting. I'll show you some videos, but it's actually very difficult for people to describe. While I'm pulling out, if there's any other questions, I'll happy to take it.
I think for the pipe example, like all these joints and how we call them, like the pipes of different sizes, we don't give them colors, but they're just different sizes. And like we have never talked about.
Oh, I have to reshare again.
The IKEA furniture.
Yep. The IKEA furniture problem. So I'll show you. When they are only used speech, it's almost impossible to describe it.
Pick the blue block that's between, pick the middle blue block and then move it towards the near, pick the middle block, middle blue block and then move it between the blue block closest to me and the yellow block.
It's very difficult, and people use different ways. Like people say, "Oh, 3 inches closer to me," that kind of like reference. But yeah, so we observe a lot of multimodal specification, and that's the direction that we're pushing. But short answer is we don't. Yeah. Yep, Carlos.
So I see that most of the experiments you use are kind of like Wizard of Oz kind of experiments. Do you see in the future using actual LLMs in your experiments, and what is missing there for you to use that? Is that even useful for you at this stage or not?
Yeah. So some of the examples are Wizard of Oz, some of them are not, right? So the assembly one is not. The one that we put into, we just finished, it's not the voice assistant, right? So one of the things that we learned, and we just submitted yesterday, is that for integrating voice assistant, Alexa skill and LLM, there's this tricky between the response delay and Alexa skill once it close. So we have to interject fillers and small talk to get the conversation going, right? So the participants will ask a question. If it takes more than 2 seconds, the voice system will say, okay, well, that sounds good. Let me get that for you. And if it's still waiting for the answer to come back more than 6 seconds, the voice system will start to engage in small talk, right? So we saw that was actually effective to get the actual data from the language model back and then translate it back. So we need to build in like engineering hacks to make that work. But for robots, not yet. But for voice assistants, I think we can do that.
I want to ask a question. I want to ask one speculative question.
Yeah.
I'm wondering if you can speculate how the broader field of AI and ACI is going to look in 5 years or 10 years.
I'm going to, anything I say will be wrong, right? Now, like last November, this ChatGPT came out just changed the way I see a lot of problems. And I didn't expect to use a lot of language in my work, but since last year, like, we integrate a lot of that into our work. So anything I say is wrong. To me, I think there'll be more embodied, more situated, more multimodal. But I think we also need to learn more about the natural way people interact and what's the mental model expectation they have, right? So even with the deployments, voice system deployments that I showed earlier with older adults locally here, we just see a lot of breakdowns. Because when people design those voice systems and skills, they don't really think about the user characteristics, right? So in that example I show, some of the older adults, they just speak slower, they have more fillers, and that will break all the auto transcription, and that will break the follow-up language request. But one of the things that we learn is also, Alexa will transcribe whatever it hears and then send that request to ChatGPT. And that transcription is wrong, and therefore all the communication after that is wrong. Right. So I think to address that, we really need to understand that people's expectation, the way people would behave in chat, and therefore we can really address that. So to me is like, I'm biased. Going back to people, understand how people will interact with your AI model and systems in a real world setup. If that makes sense.
Open-ended question. I don't know how anyone would answer it, but what is known about people interacting with some entity and knowing that it's another human being versus knowing that it's a machine? Wizard of Oz was a good example that although the front-facing thing looked like a robot talking to you, the script probably knew that there was somebody at the back typing or so on. Or maybe there isn't. So do you know how humans react differently to humans versus machines? And many aspects. One is just in the telephone dial area, I've seen people swearing a lot more at computers than another human agent.
Yep.
But on the other hand, they're also, in a strange way, more trusting of what computers understand.
Yeah. No, I think that's a good point. That main interrupting voices example, that part will not happen if that's another person sitting next to you, across the table to you, right? Just people have this behavior change because of the modality, because of the embodiment that they're interacting with. But Wizard of Oz is, it's a pretty good methodology for us to really understand if this happened, if this actually is a reality, what people would behave. But yeah, there's generally some behavior shaping because of whether or not they believe they are interacting with person versus machine. Another thing that we learn is, for a lot of this study, you need to take people out of it, right? So if you are observing their behavior, participant will behave differently as well. Yeah, so those are just general research methodology that we would build into the process.
Speak a little to the distinction between how people do interact with systems versus perhaps how they should interact. And then, so I'm thinking about this particularly in the context of the small talk that what is the sort of, is it actually constructive for people to interact in small talk while they're doing these tasks? What are the longer term effects of that, regardless of whether or not in the moment they would actually respond?
Yeah, so good question. What would be the ideal interaction versus what would be natural? So the way I think about this is we don't necessarily have a set of ideal interaction or expectation from the way people will interact with the system. So a lot of our first stage of research is to understand the natural people behavior and reactions. But toward the end, I talk about the structure, putting some structure to help to improve the interaction. That's where I think the expected behavior would happen, right? So if we want to constrain the rich interaction space, then we will need to put structure, and therefore we will have some expectation for the person to behave. But yeah, for small talk, we don't necessarily know about a lot of things that I talk about today. We don't necessarily know about their long-term effects, right? So the closer one will be the deployment that we did with local older adults. But still, it's like, only 4 weeks. We are not even looking at, over 6 months or a year. Yep, Jason.
So I just want to ask a little more broadly about the types of collaborative tasks that you're trying to build assistants for, or collaborators for. So what is the model that the system has of the task, and how flexible is it? And, there must be a lot of traditional AI, I'm guessing, going on inside the system about planning and replanning based on what the human does, maybe inferring beliefs, desires, intentions. That phrase, beliefs, desires, and intentions, comes from the natural language dialogue communities where I've seen it, but maybe you use it as well.
Yeah, so there's no one set context we build off. Right? If you look at the example I show you, they are all from slightly different context and application domains. But what we're really interested in is the interaction dynamics. Right. So for the assembly task, the text model is fixed in our setup. Right. So we have a pretty good sense of what the final assembly assembled product will look like, and therefore we have a model. So we are not working at the model level. Like, because to me, I think that itself is its own research agenda. Like, we assume we have a model, and then use that model. How do we understand the dynamics?
Right, but when you say model, what does the model consist of?
Right. So, for example, it will be a structure. Right. So if you start with this pipe or this joint, what might be possible next? Right. So think about it as a tree. Yep.
So basically, the model is the target structure.
Yep.
And the dialogue is saying we built part of it, and then you're doing traditional planning.
Yep.
Like
So
to say you're a possible next boost.
Yeah. So if you're down the tree in this node, what might be possible actions, and what can you say here? Yep. So that tree structure is pre-given. We are not building that from scratch.
And sorry, why is it a tree structure?
It doesn't have. We just use tree because if you think about that assembly, you can start with any node or any piece of things, and then you start to build up. Right. So it could be a joint and different kind of pipes. Once you get this pipe, you can do that. But
suppose the thing that you're building is a square. Like a pipe loop.
Yeah.
So I'm not sure how to decompose that into a tree.
Yeah, it doesn't have to be a tree. I'm just like describing it as.
Awesome. I don't see any other hands. So let's thank Chien-Ming one more time.
Well, thank you.